Let's talk about heat. It's this invisible force all around us, right? It warms our coffee, it's what makes our air conditioners work, it even drives the entire planet's climate. We feel it every single day, but what is it really? Okay, we're going to dive in and uncover the simple rules that govern this whole unseen world. So to get us started, here's a little puzzle to chew on. You've got a thick, fluffy wool sweater. It keeps you warm by trapping your body heat. Makes sense. But then you have one of those paper-thin, foiled emergency blankets, and it does the exact same thing. These materials are polar opposites, so how on earth do they both work? Well, by the end of this, you're gonna know the answer. So here's our game plan. First, we'll clear up the #1 biggest confusion, the difference between heat and temperature. Then, we'll get into the secrets of why materials act so differently. We'll talk about the weird paradox of melting ice, figure out how heat actually moves around, and then we'll wrap it all up with the key rules.
All right, first up, we have got to tackle this one. We say heat and temperature like they're the same thing all the time, but in the world of physics, they're completely different. I promise you, getting this right is the key to understanding everything else we're going to talk about.
Okay, here it is, the big difference. Temperature is all about intensity, but heat is about the total amount of energy. Think of it like this. You could have a tiny little jacuzzi that's super hot, right? Say 40 degrees Celsius. But a massive Olympic-sized swimming pool that's just lukewarm, maybe 25 degrees, contains way more heat. Why? Just because there's so much more water. The pool has way more total thermal energy it could give away. So, to get a little more technical for a second, temperature is really just about the average speed of all the little particles. When something feels hot, its molecules are just vibrating and zipping around like crazy. When it's cold, they're moving a whole lot slower. So, temperature is basically a measure of that molecular hustle. Heat, on the other hand, is that energy in transit. It's the flow of energy from something hot to something colder. And this flow just keeps going until everything is the same temperature. That's what we call thermal equilibrium. So the key is, heat doesn't just sit there, it moves. So now that we're clear on what heat is, let's figure out why it affects different things in such different ways. I mean, why does a metal spoon you leave in hot soup get scorching hot almost instantly, but the soup itself takes forever to cool down? The answer is this really cool property called specific heat. Specific heat capacity. It's kind of a mouthful, but you can think of it as a material's thermal stubbornness. It tells you how much energy you have to pump into something just to get its temperature to go up by 1 degree. So something with a high specific heat, it really resists changing temperature. And the difference between materials is just massive. I mean, look at this. Water has a crazy high specific heat. It's more than 9 times higher than iron. That's exactly why it takes so long to boil a pot of water, but it's also why that hot water stays hot for a long time. Metals, on the other hand, with their low specific heat, they heat up and cool down super fast. And this isn't just some random science fact. This stuff literally shapes our world. The huge specific heat of water is the reason cities on the coast have much milder weather than places inland. The ocean acts like a giant thermal battery. And it's also why our frying pans are made of metal, right? We want them to get hot fast. Okay, this next idea is a bit of a mind bender, so stick with me. We just established that when you add heat to something, its temperature goes up. But what if I told you that's not always true? Sometimes you can pump a ton of heat into something and the temperature won't change one bit. So let's imagine this. You've got a block of pure ice and it is sitting right at 0 degrees Celsius, its exact melting point. Now you start adding heat. What do you think happens to the thermometer?
Well, if the ice starts out really cold, say -5, the heat will raise its temperature, just like you'd think. But the second it hits 0 degrees Celsius, something weird happens. As the ice starts to melt, the temperature just gets stuck. It stays flat at 0, even as you pour in more and more energy. All that energy is busy breaking the bonds holding the ice crystals together. It's only after every last bit of ice is melted that the water's temperature will finally start to climb again.
This hidden energy actually has a name. It's called latent heat. It's the energy that's needed to change the phase of something, solid to liquid, liquid to gas, without actually changing its temperature. It's the energy of transformation, not the energy of motion. And this concept has a really dangerous side. For example, a burn from steam at 100 degrees Celsius is way worse than a burn from boiling water at the exact same temperature. And why is that? Because when that steam hits your skin, it first has to release a huge amount of latent heat just to turn back into water. And then you've got the 100-degree water. It's like this devastating 1-2 punch of thermal energy. Okay, so we know what heat is, and we know some of its really weird behaviors. But how does it actually get from point A to point B? Well, it turns out there are 3 main highways for energy to travel.
These 3 methods are conduction, convection, and radiation. Pretty much every time you feel heat moving, it's some combination of these 3, but each one works in its own very distinct way.
Let's break these down real quick. Conduction is just heat transfer by direct touch. Imagine a line of dominoes. One vibrating particle bumps its neighbor, which bumps the next one, and on and on. That's how the handle of your pan gets hot. Then there's convection, which is heat moving through flow. When you heat up a fluid, like air or water, it expands, gets less dense, and rises, taking the heat with it. Colder stuff sinks to take its place, and you get this circular current. And finally, radiation. This is pure energy, traveling as waves, and it's the only one that doesn't need any stuff to travel through. That's how the sun's warmth gets to us through the empty vacuum of space. And that brings us right back to our starting puzzle. Radiation is the key here. So a wool sweater works mostly by trapping a layer of air next to your body, which stops heat from leaving through convection. The wool itself is also a bad conductor. But that shiny foil blanket? It works on a completely different principle. It's an amazing reflector of thermal radiation. It literally bounces your own body heat right back at you. So there you have it, 2 totally different methods, but the same warm result.
All right, we've covered a ton of ground. Let's just take a second to boil it all down to the most important rules you really need to remember.
Seriously, if you remember anything from all this, make it these 4 points. Number 1, heat is energy flowing. Temperature is just molecular speed. 2, specific heat is thermal stubbornness. Water has a ton of it, metals have very little. 3, melting and boiling happen at a flat temperature because of that hidden latent heat. And 4, heat moves by touch, by flow, and by waves. Conduction, convection, radiation. And I'll leave you with one last thing to think about, to see if you can apply what you've just learned. A thermos is just a master of thermal control. It keeps your hot coffee hot for hours, but it can also keep iced tea cold on a blazing summer day. So thinking about conduction, convection, and radiation, how exactly does it pull that off? The answer lies in how it blocks all 3 of those heat highways. Think about it. Thanks for joining me.